Hello everyone, this is the second part of the previous video of microstrip patch antenna design and analysis in HFSS. So in this part of this video I will show the analysis, that is plotting the results, the S parameters, the radiation patterns of this rectangular patch antenna. So this is the rectangular patch antenna designed in the previous video. So to define the far field of this antenna, I have to design a radiation box. So draw a 3D box. Okay, so arbitrarily I have taken a 3D box, and now I will assign the material and the dimensions of this box. Now what will be the dimension of this box? There is no specific dimension of the radiation box. The main thing is that the total design, the complete design of this antenna should come inside this box. No part of the design can be outside this box. Okay, so accordingly you have to design this box, and this box is actually to define the far field of this antenna. Okay, so first of all I will assign the material. So by default it is vacuum, but for more practical results I will assign it as air material. Okay, and also I will make it transparent up to 80% for the better visibility of the other parts of the antenna. Okay, so what will be the dimensions? Dimensions will be similar, and it should be according to that, so that the complete antenna comes inside this box. So this is 13.19 by 2 minus 3 into 1.6 minus 10 mm. Okay, and the y coordinate is minus 17.54 divided by 2 minus 3 into 1.6 minus 10. This is minus 1.6 minus 10. And what will be the x size? This should be 13.19 plus 6 into h plus 20. The y size should be 17.54 plus 6 into 6 into h plus 20, and the z size should be 1.6 plus 20. Click on OK. Now see, the complete antenna is lying inside this box. Okay, now by clicking this option you can check which part of the design is over and which parts are remaining. So see, the design part is almost done. Now I have to assign the boundaries, conditions and the excitations, and also the analysis setup. So let's put the boundary conditions first. So I am assigning the boundary condition for the patch first. So select the patch, then right click, then assign boundary, and select it as perfect electric. Okay, now select the ground. If it is not selected from here, you can rotate it like this, then you can select the ground plane. Select, right click, assign boundary, make it perfect electric. So boundary condition of the patch and ground is given, and also have to give the boundary condition for this radiation box. Select, right click, assign boundary, and give it radiation boundary box. Okay, so boundary conditions are given. Now I have to give the excitation. Now I have to excite this excitation plate. Okay, that is the port plate. So for that I have to select this plate first, then right click, assign excitation, and we are giving lumped port here. So click on lumped port, this window will come. Click on next, then select here. You have to select an integration line to give the excitation. So for that you click on none, and here you select new line, then choose a point in between the below line, then give the integration line like this. Okay, so the integration line is defined, then click next, click finish. So the excitation is given, the boundary conditions are given. Now I have to give the analysis setup. So for that, click on HFSS and select this option, analysis setup, add solution setup. So the solution frequency is nothing but the operating frequency of this antenna, and it is 5.2 gigahertz. Select OK. Now you have to also give a frequency sweep for this setup. So add frequency sweep. So the sweep type you can put it interpolating, but I will make it fast for less execution time. And the start and stop frequency you can assign from here. The stop frequency I will give 7 gigahertz, and the step size I will put 0.1 gigahertz. So select OK. Okay, now you check everything is done. Now you can start the simulation of this antenna. To simulate this antenna, you can simply click on this option, that is analyze all option, or you can also find this option from here, HFSS analyze all. So I will use this shortcut, click on analyze all. So first you have to save this design, and when you will save, it will automatically start the simulation. So the simulation will take some time, but I will fast forward. So the simulation is done. Now I will plot the results one by one. So first of all, I will plot the scattering parameters. So there is only one port, so there is only one scattering parameter, that is S11 parameter, which is known as the reflection coefficient of the antenna. And if I plot this reflection coefficient in dB, it is also called return loss of this antenna. So for that, you click on HFSS, go to results, create model solution data report, then rectangular plot. Here you can see, select the S parameter, then select S11, then select dB, click on new report. So this is the reflection coefficient of this antenna. So see, the antenna is resonating near this assigned frequency, but the reflection coefficient is not coming well. For general operation of the antenna, it should be, the reflection coefficient should be below -20 decibel, but it is not coming properly. So this is because of the impedance mismatch. So for that, you have to do some modifications in the design. So here we have given the microstrip line feeding. Okay, so for microstrip line feeding, inset feeding is required for impedance matching. Okay, so inset feeding is nothing but you have to insert this feed line inside this patch. Okay, so for that you have to cut from here and here for insert feeding. Okay, so for that you have to draw a small rectangle here and here, then you have to cut out these rectangles from this patch for impedance matching purpose. So let's do this. So first of all, I will delete the solution first. Result, cleanup solutions. So I will design a small rectangle like this, and also I will assign the coordinates accordingly. This will be 13.19 divided by 2, and see, the x size is nothing but the depth of this insect feeding, and the depth you can choose by trial and error method, and also you can choose this depth by parametric analysis. I will show this in my next video. Okay, so for proper impedance matching you have to choose this depth. Okay, so I am putting here the depth 4.8 mm, and y size is nothing but the width of this gap, that is the gap. So I am putting it 0.5 millimeter. So click on OK. So the small rectangle is designed. Now the same rectangle I need here also, so I will not design again, I will just make a duplicate of it. For that you select it, right click and click on edit and duplicate, and select along line. Select any vertex of this small rectangle and select a particular line, and I need here 2 copies in total, so the total number you put 2, then click OK. Now the move vector you can modify from here because it is not moved properly, so the move vector you have to modify from here. Click on this duplicate, double click. So what should be the move vector? See, this is moving along the y-axis only, positive y-axis, and there is no movement along the x-axis and z-axis. So the z coordinate, z vector should be 0, and the x vector should also be 0. And what will be the y movement? This should be 3 plus 0.5, that is 3.5. Click on OK. Okay, so these small rectangles are designed. Now I have to subtract these 2 rectangles from this original patch. So for that you select the patch first, then press and hold the control key, select the 2 rectangles and click on this boolean option, subtract. Okay, so this is done. So this is looking like an insect feeding of microstrip patch. Now I will run this design again. I will again simulate this design for results. So click on simulate. Again it will take some time, but I will fast forward. Okay, so the simulation is done. Now I will plot the results one after another. So first of all I will plot the reflection coefficient. So for that click on HFSS, results, create solution, data report, rectangular plot, then S parameter S11 dB, new report. So see, now the impedance is properly matched and it is below minus 30 decibel. The requirement was minus 20 decibel, but it is below minus 30 decibel. So it is properly matched, and the frequency you can see this is around 5.2 gigahertz. Okay, so this is the reflection coefficient, and the bandwidth you can also calculate from here. The definition of bandwidth is that you have to notice the minus 10 dB line, and you have to note these 2 points from here. The minus 10 dB line is cutting this plot here and here. So here what is the frequency? You can see the frequency from here. Okay, so put the cursor here, make it minus 10 decibel, and notice the corresponding frequency, it is around 4.9 gigahertz. Okay, and put the cursor here also, and here the frequency is around 5.2 gigahertz. So what is the bandwidth? The impedance bandwidth is 300 megahertz. So here I am getting an approximate impedance bandwidth of 300 megahertz. Now we'll plot the radiation characteristics. So to plot the radiation characteristics, first you have to give a far field setup. Okay, so to give the far field setup, you have to click on this radiation option, and here right click and select this option, insert far field setup, and select infinite sphere. So here the range of phi and theta you have to define. The range of phi you can give from 0 to 360 also, but I will give from minus 180 to plus 180. So this will make a symmetric radiation pattern. Okay, and the step size you can put it to 5 degree. Okay, and the range of theta should be 0 to 360. Okay, step size is 5 degree. Click on OK. So the radiation setup is given. Now click on HFSS, results, then the far field report, and here you select this option, 3D polar plot, and here select gain. You can plot directivity also, but I am plotting the gain now. So gain, select gain total, then select dB from here, and click on new report. So this will plot the radiation pattern of this antenna. So here you can see this is a directive radiation pattern, and the direction of maximum radiation is along the positive Z direction, and you can also note down the gain from here. So the peak gain of this antenna is coming around 4.5 decibel. Okay, now I can plot the 2D radiation pattern also. So to plot the 2D radiation pattern, you click on HFSS, results, create far field report, then radiation pattern. So here select gain total, then dB, and from here you click families. So first of all I will plot the E-plane radiation pattern. So if you are plotting E-plane radiation pattern, the phi value should be set to 0 degree. So you set phi to 0 degree for E-plane radiation pattern. Click new report. So this is the E-plane 2D radiation pattern. Now I will plot the H-plane radiation pattern also. So for that click HFSS, results, create far field report, results, far field report, radiation pattern, gain total, dB, click families, and now for H-plane radiation pattern you have to choose phi equals to 90 degree. So click here and set it to 90 degree. Click on new report. So this is the H-plane 2D radiation pattern. So total 4 things I have plot here. the reflection coefficient plot, and also have calculated the bandwidth, which came 300 megahertz, the 3D radiation pattern along with the peak gain, that is 4.5 decibel, then the 2D E-plane radiation pattern, then the 2D H-plane radiation pattern. So thanks for watching. See you in my next videos. Thank you.